Hello, Chem 104 students. Okay, so I'm out of town early next week, so I'm making you this video. For one of my courses, this is a review. Tuesday, Thursday class, you've already seen a weak acid strong base titration. I'm using the same example I used in class, but I think I've chosen a few different volumes. So it might feel redundant, but I think you could all probably benefit from watching this a few more times. Monday, Wednesday, Friday, you have not yet seen a weak acid strong base titration, so buckle up. It's a lengthy process. This is going to be a really long video. It's a step-by-step tutorial, so pause it when you need to. I've broken it down so each slide is looking at a different volume of base added. So, stop it when you need to, review, solve again. I don't know. You'll be all right. Have fun. Okay, so weak acid strong base titration. The chemistry gets a little bit more intense than a strong titration. So we're going to consider the titration of a 50 milliliter volume of 2 molar HNO2. So weak acid. We know it's a weak acid because it's not one of our 6 strong acids, which you should have committed to your memory by now. We also know it's a weak acid because we see a Ka there that's given. So when we see a Ka, we know that it's only a partial dissociation that reaches equilibrium. We're going to titrate that weak acid with strong base. So we have a 1 molar solution of potassium hydroxide. So we'll imagine we have a beaker, and in that beaker, no, that's not the right beaker. That's the beaker. Sorry guys, I'm alone in my office on a Saturday. I've been doing this for hours. So I got bored and I love beakers. So in that beaker, we're going to place 50 milliliters of 2 molar HNO2. And we're going to titrate into that beaker 1 molar of KOH. So we're going to solve for 4 separate pHs along this titration curve. The first pH we're going to solve for is the initial acid in the beaker before we ever add any potassium hydroxide. So just what is the pH of this 2 molar HNO2. Then we're going to find the pH of the solution after we add 50 milliliters of the base. So we'll put in 50 milliliters of hydroxide, changing the volume in the beaker and forming a new pH in that solution. Then we're going to find the pH of the solution after the addition of 100 milliliters of base, and then we'll find the pH of the solution after we add 150 milliliters of base. Now, none of these say that they're the equivalent point, the equivalence point, but one of them is the equivalence point. If we didn't know where the equivalence point was, all of the classes have seen this calculation. You can find the volume of base needed to reach the equivalence point. We did this in class in all of the examples. You could take the molarity of the acid times the volume of the acid, set that equal to the molarity of the base you're using times the volume of the base needed to reach the equivalence point. In this case, the unknown is the volume of the base, so you could plug in and solve. I'm not going to. You could go ahead if you felt so inclined. You could figure out where the equivalence point would be for this particular titration. Okay, so first we're just going to find the initial pH of the acid in the beaker. So we haven't added any potassium hydroxide. What we have in the beaker is just a weak acid. So to find the pH of a weak acid, right, we need an ICE chart, we need an equation, and we need a case statement. Right, so that's some old stuff from the last chapter. It'll be a nice review as we head into the third exam. So we need a governing equation. The weak acid in the beaker's just able to bump into some water. There's nothing else in there for it to react with. It can undergo an equilibrium reaction of dissociation. We're not changing the volume. It's just hanging out in its 50 milliliters. And so we'll deprotonate that acid, forming H3O+, and leaving behind the conjugate base of the acid, NO2-. So you should feel pretty comfortable in writing that governing equation, and you should feel comfortable in selecting an ICE chart in order to solve for the pH of the system. We, of course, don't care about water, but we do have to go about filling in everything else we know about the weak acid. We know that the initial concentration is 2 molar. Remember, molarity can go into an ICE chart because the volume is constant. So molarity can go in. We've got 2 molar here. We're going to lose some amount, but again, we don't care about that change because K is small. So we have this initial concentration that is also our equilibrium concentration of HNO2. Initially, we don't have any H3O plus or NO2 minus in the beaker. After this is established equilibrium, we know that we're going to add some unknown amount of H3O plus and NO2 minus. We know that they're both going to be X because these stoichiometric coefficients are both 1. So we have 1X and 1X. 0 with the addition of X gives us an equilibrium concentration of X in both of these columns. We need Ka. The Ka expression here says that we need to do X squared divided by the initial concentration 2 molar. So now I can just plug in. I've got 4.0 times 10 to the negative fourth is equal to X squared over 2.0. Sorry, that looks crazy. 2.0. Okay, so if I rearrange this and isolate X, X will be equal to the square root of the 4 times 10 to the negative 4 times the initial concentration. That X, I want to remind myself, is actually equal to H plus. So because I'm in an acid solution, when I find X, I will have found H plus or H3O plus. Those are synonymous. I found my hydroxide concentration to be 0.02828 molar. So check your math, calculate along at home. If we know that's the molarity of our H3O plus in solution, we can find our pH by taking the negative log of that value. And I found the pH of the system to be 1.55. So that is my initial pH before we've done any titrating of this sample. So that's the pH that we're going to start with. Okay, so the next step is to add some base. So we're going to add 50 milliliters of base, right? We have to keep track of this volume change. We have 50 milliliters of HNO2 in this beaker already. When we add in 50 milliliters more of the base, we will have a new total volume of 100 milliliters, right? That's important because when we change the volume, we can no longer rely on molarity to tell us about what's going on in this beaker. Molarity changes as volume changes. So we're going to react to strong base. We need a governing equation, and we're not going to be able to track molarity, so we're likely going to not be able to use an ICE chart. My governing equation says that my hydroxide, the thing that I'm adding in my titration, is going to react with the only other compound in that beaker. These governing equations are easier to write than buffers. There's nothing to choose here. It's the thing you add plus the thing that was already in the beaker. Now, that's not going to reach equilibrium. I've chosen a very big forward-moving arrow here. This guy's strong, and he's not going to stop until he's totally neutralized. Right? So we've got a base acid neutralization going on. We will produce NO2 and H2O. This hydroxide goes over, snags that hydrogen and makes water, and leaves that NO2 minus behind. Okay, so there's the governing equation. We know we're going to need some kind of chart to keep track of this math. Again, no equilibrium, no ICE chart. I can't use ICE here because my equilibrium is not reached and also my volume is changing. So I'm going to make a chart, but it's going to be before addition, after chart. Now these guys, as we've already said, have to have moles as the units. So before I can start any of this, I need to calculate my moles. My moles of HNO2 is my molarity times my volume. I had 50 milliliters or 0.5. I don't obviously know how to erase with this little guy. Nope, no idea. Okay, 0.5. No, it was. Oh boy. 50 divided by 1,000 is 0.05. Rob, are you fixing this at home? You're probably cringing. Okay, I've done it. So when you multiply these things together, you're going to get a concentration of 0.10 molar of HNO2. That's an important number because every time we change the volume of base that we add, right, we're always going to assume that we're starting with this amount of acid. always 50 milliliters at 2 molar. So we're always going to start with 0.1 molar HNO2 for each of the subsequent calculations. So this is 0.10 molar or moles, right? So that's what I have initially. Okay, now before we put in the hydroxide, before we add the 50 milliliters of base, we don't have any base floating around. And before we do this, we don't have any NO2 minus, and we don't really care about H2O. Oh wait, nope, just kidding. We don't really care about H2O. Now, we've added the base. So I go into the base column, and I need to report how many moles of base we've added. We added 50 milliliters of 1 molar base. Let's see if I can do this one a little more smoothly. So I want moles of hydroxide. So I'm going to multiply the 1 molar by 0.05 liters, giving me 0.05 moles of OH minus. So I go over here and I record that. I have 0.05 moles that we're adding. Okay, this is a forward moving reaction. One of these two reactants is going to have to be completely consumed. This guy is my limiting reactant because I have the smallest amount of hydroxide. I have more acid. So this guy's going to go to 0. I'm going to lose 0.05 moles of this because he had to go over there and neutralize the hydroxide. So I have 0.05 moles left. If I subtract those two values, I have made 0.05 moles of NO2 minus. My stoichiometry is 1 to 1 to 1. So I have 1 unit of 0.05, 1 unit of 0.05, 1 unit of 0.05. I'm losing it in this reactant column and I'm gaining it in the product. Okay, so I had none. I added 0.05, 0.05. Okay, what is floating around in this beaker right now at this moment? After the addition, if I check out what's happening in this row, I don't have any strong base. I have a weak acid, and I have its conjugate base. What do we call a weak acid and its conjugate base? If you don't know, email Deb, she'll tell you. It's called a buffer, right? This is the definition of a buffer. So during a strong, weak titration, you make a buffer. And how do we find the pH of a buffer? We go to Henderson-Hasselbalch. So that's not so bad. Okay, so these are moles. I need to convert moles to molarity. So molarity is equal to moles over liters. I'm going to take my moles and I'm going to divide by my liters, which I said over here I had 50, I added 50, I now have 100 milliliters, or 0.10 liters. Happens to be the same. I have as much weak acid as I produced weak base. So this calculation is going to be mathematically the same. Moles over liters. They're in the same volume floating around. Okay, so this molarity for my weak acid is 0.5 HNO2. And this molarity is also equal to 0.5 NO2 minus. So we said we find the pH of a buffer by using Henderson-Hasselbalch. That tells me that pH is equal to pKa plus the log of the base over the acid in the buffer. I know my Ka, it's given in the problem. If I take the negative log of this, which is what pKa means, right? It means negative log Ka. I get that value to be, oh, I didn't write it down. Let's just calculate it now. It's just like we're in class, and you have to watch me do my work at the board. 3.39. So this guy's 3.39. It's really 398. And then we're going to add the log of the base over the acid. Turns out the base acid concentrations are the same. The log of 1 is just 0. So our pH, after the addition of 50 milliliters of 1 molar potassium hydroxide, is 3.398, which we'll just call 3.40. So initially the pH was 1.55. I added some base, and the pH is beginning to creep up. That's what it should do, right? Because we're adding base, we're becoming more basic or less acidic. So that is the calculation for a strong weak titration when we're adding beneath the equivalence point. We have not yet reached the equivalence point. Okay, so now we're going to move on to part C. In part C, we said let's add even more base. Let's add 100 milliliters of this base. We're going to revert back and assume we still have this 50 milliliter volume of 2 molar. So the moles are going to be the same. Let's see if I can do it this time. It's going to be molarity times the volume in liters. It's going to be the same value that we had on the last slide, but I kind of made a mess of it. So 2 molar times 0.05 liters gives me 0.10 moles of HNO2. Okay, so we're going to need the governing equation again. The thing that we're adding plus the thing that's in the beaker. So our weak acid, again, a big forward moving reaction here. No equilibrium, the volume's changing, we're producing the anion and some water. We're going to need a before addition after chart because the volume is changing and we're not at equilibrium. And now I go through the process of filling out my chart. Before we add the hydroxide, there's no hydroxide. Before we do the reaction, there are no products. I need to know the moles of HNO2. We're assuming it's still our initial set of conditions, 0.10 moles. Now, we're going to add 100 milliliters of 1 molar potassium hydroxide. So to find the moles, I take my molarity and I multiply by my volume in liters. My moles are 0.10 moles of hydroxide. That's what we added. Where are we at? Who is the limiting reactant here? I have exactly the same amount of base as I have acid. These guys completely consume one another. There is nothing left on the reactant side. All of the acid has been consumed. All of the base has been neutralized. They're gone. How much NO2 minus did we make? The stoichiometry here is 1 to 1 to 1. If I added 0.1 molar OH, or I'm sorry, moles OH, I made 0.10 moles nitrite, NO2 minus. So this is what I have left floating in my beaker because nobody cares about water. This is the only thing floating in the beaker at the equivalence point. This moment is the equivalence point. So I have moles of NO2 minus. I divide that by my volume. Remember, we added 100 milliliters. I now have 150 milliliters. So I go over here and I divide by 0.150 liters. My molarity of NO2 minus is 0.667 molar. So in this beaker, at the equivalence point, the only thing that's hanging out is the conjugate base of my weak acid. So I have a weak base. And how do we find the pH of a weak base? We need an ICE chart. We need a governing equation. And we need a KB. We don't have any of those things right now. So we're going to have to write a governing equation for this weak base bumping into water. We're going to have to draw an ICE chart, and we're going to have to solve for KB because I only know Ka. Let's continue on the next slide so I have some space. So there's the weak base. We have to remind ourselves we had 0.667 molar of NO2 minus just floating around. The Ka was 4.0 times 10 to the negative 4. Okay? When NO2 minus bumps into water, you have to be able to write the governing equation for a weak base. He's going to take the hydrogen from water. He will be able to reach equilibrium, and he will produce a hydroxide. Remember, water is just HOH. He's going to snag that H, producing the weak acid and the strong base. When we make hydroxide, we are going to need Kb. Oh, I'm writing in a place that I shouldn't be writing because I don't know how to erase. But okay, so I'll stop. So there's my ICE chart. I'm going to have to find Kb. Remember, Ka times Kb is equal to Kw. So if I rearrange that and plug in for Ka, I know Kb. Kb for this NO2 minus will be 2.5 times 10 to the negative 11th. From that, I can continue on and do all of this work. So I know my concentration. I got it from my before addition after chart. There is some amount of change, but I have a very small Kb, so I don't care about that. I'm going to allow the equilibrium value to be the same as the initial. I don't care about water. I do care about hydroxide. Now, I fucked up and drew there. Oh, now I'm cursing on a video. Oh, goodness, it's all unraveling. Okay, I have no hydroxide initially. I make some amount of hydroxide during this reaction. I had none. I made X amount. At equilibrium, I have X amount. Initially, I had no weak acid. I made X amount of weak acid. I can solve for X. Now I have my ICE chart. Now I can plug into a Kb expression. So 2.5 times 10 to the negative 11th is my Kb. That's going to be equal to X squared over my initial concentration. Remind yourself here that X is hydroxide. If you use a Kb, you're probably finding your hydroxide concentration. So when we find X, I can multiply those, take the square root. I found X to be equal to 4.06 4.08 times 10 to the negative 6th. That is my hydroxide concentration. So if I take the negative log of that, I can find POH. POH in that case is 5.38, I think. I'm calculating. You all can't see it. Yes. 5.38. The pH then is 14 minus 5.38. That gives us a pH of 8.61. That's a lot of work to find the pH of a strong weak titration at the equivalence point. We had to do the BAA chart. Oh, that's never going to work. We had to do the BAA chart, which yielded who was remaining at the equivalence point, which was the conjugate base. Then we had to bring that conjugate base forward and study its equilibrium condition in order to find the pH. A lot of work there, so you're going to have to review these steps, watch this video, bring any and all questions that you have to class, either on Wednesday or Thursday of next week. Okay. I'm sure you guys are having as much fun as I'm having. All right, so now we're going to add 150 milliliters of base. So we're adding even more. So now we're going to come over here and add 150 milliliters of base, so that my total volume will be 200 milliliters. Again, I'm now back to adding hydroxide to my weak acid, so I need a governing equation. The hydroxide bumps into HNO2 just like it did in parts B and C. It's going to deprotonate that hydrogen in a forward reaction, producing the conjugate base and water. I'm going to need a chart, and because volume is changing and hydroxide is strong, I can't use an ICE chart, so I use a before addition after. Now, this is still holding steady at 0.10 moles from all of our earlier calculations, right? We're always going back to initial, we're resetting these calculations. So before I added hydroxide, I don't have any. Before I added hydroxide, I had 0.10 moles, and I never have any of my products. We added 150 milliliters, so now we've got to do this math. To find the moles, I multiply the molarity by the volume in liters. I now have 0.150 moles of hydroxide. I can plug that in. Now I have to carefully assess who my limiting reactant is. I have a smaller amount of acid now. My acid is totally consumed, right? He will go to 0. He's gone. I will subtract that amount. I always subtract my limiting reactant from my excess reactant. I want a positive number here. Okay? If you're getting a negative number, you're just putting them in the calculator the wrong way. I subtract my limiting from my excess. That's going to give me 0.050 moles of hydroxide. I make I can only make as much product as my limiting reactant allows. I can only make 0.10 here. I know that usually we go by the addition and we would run that number across the table, but we have to watch out and only use as much as our limiting reactant can make. So this guy's going to set the tone here. Okay, so he's going to be here. That's how much of this I can make. I don't care about water. So he's going to be 0.10. Now, what I have in the beaker right now, I have strong base and I have weak base. We are okay to neglect the weak base. This guy's really going to control pH. This guy's a weak, oh goodness, no. Weak base. Bad job, Dr. Fuller. The strong base is going to set the tone for the pH. He's going to control the hydroxide concentration in the solution. We're okay to neglect the effects of the weak base. So, if I divide these moles by my new volume, 0.20 liters, I'm going to find that I have a molarity of hydroxide equal to 0.25. I don't think there's a 0 there. 25 molar. So, if I know the molarity of my hydroxide, I can just find the pH of this by finding the pOH first, right? I have my hydroxide, I have to find my pOH to find my pH. So, I'm going to take the negative log of the hydroxide. I'm going to find the pOH to be 0.603, which is going to allow the pH to come out highly basic, which is what we want, at 13.39. Each step of this titration required a different treatment, right? So let me explain what I mean. In part A, it was just a weak acid in solution. And so we had to solve pH for just a weak acid. So we found the pH by making a governing equation, making an ICE chart, and using Ka. So that's what we do when it's just the weak acid. In part B, we were under the equivalence point. We had not reached the equivalence point yet. In a strong weak titration, right, with a weak acid, strong base. When you're under the equivalence point volume, you're going to make a buffer. And then you're going to have to use Henderson-Hasselbalch. So that was like calculation B. Calculation C, that was at the equivalence point. When you're at the equivalence point, you're going to have to make a before addition after chart, and then use that concentration to make an ICE chart. So you'll make an ICE chart from there. And then you'll need the governing equation and the chart and Kb. So that was a huge calculation that we did, took up 2 slides for part C. And then when we over titrate beyond the equivalence point, we will be in a hydroxide dominated solution, because we are adding a strong base in this scenario. When we have a hydroxide dominated solution, we can just find pOH. And that leads us to pH. We figure out that we're in a hydroxide dominated solution by doing a before addition after chart. So in each calculation, we have to look at the before addition after chart. It's just what we do is different. So we did a before addition after chart in calculation B. We made a buffer. We went to Henderson-Hasselbalch. If we do a before addition after chart and we're at equilibrium, we're at the equivalence point, then we need an equilibrium chart. And if we over titrate, we still have to do the before addition after chart. We see we're in a hydroxide dominated solution, and you find pH. Weak, strong titrations are essentially a culmination of everything you've learned in chapters 16 and 17 so far. It's everything about acids and bases that we can think of. When we make a buffer, we're really dealing with salts. When we need Kb, like, it brings in all sorts of other crazy stuff. So the likelihood of me being able to ask this question in its entirety on an exam is unlikely. But you have to understand the process, because I'll certainly ask you to find the pH of a weak acid on an exam. I may very well ask you to make a buffer on an exam, and this is a nice example of how to make a buffer. I could ask you to calculate something at the equivalence point. So you have to understand where you're at during a titration process so you know which approach will be required of you. So those of you in Tuesday, Thursday already saw this example, although I used slightly different values. Monday, Wednesday, Friday, I know you've never seen this, so it's a lot to digest, but spend Monday, when you should be in class but are not, spend Monday watching this video as many times as you can or need to in order to solve these types of problems. I will post to Blackboard some practice problems so that you can consider different questions and apply these rules to new scenarios. So stay tuned. I'll send you an email, and if you have any questions, of course, shoot me an email back, and I'll help you out as much as I can from Pittsburgh. Have a good weekend.